Thank you. Thank you very much to the organisers for the invitation to speak here. I apologise for my voice. I've been fighting a cold, and that makes my accent sound even worse than usual. This is joint work. I'm going to have a talk in 3 parts, and this is joint work with a collection of people. So Michael Dennis, who's a PhD student of mine, and joint with Shane Keating at my university. Oliver Junger, who's at TU Munich. Simon Lloyd, who's a former postdoc. Chris Rock, who's a current PhD student. Kostas Sakellariou, who's a former postdoc, and Narrative, who's a former postdoc now at Surrey. Part 1 is going to be on random dynamical systems, and I know that Michael Gill is going to say something about this later, so I'm not going to say too much, just the basics. The setup for this is probably going to be similar to what Michael is going to talk about. It's the standard setup. You have a driving system, which is some probability space, omega, and on that space, I have some transformation sigma, which is very general and deliberately general. So it's invertible, it's what's called ergodic, and it preserves the probability measure p. And you should think of omega as some kind of configuration space. Maybe this space is very complicated, and in practice you may not need to know too much about it. You think of sigma as evolution of configurations with the passage of time. So if you want a concrete example, if you think about the collection of all physically realizable high and low pressure systems in the atmosphere, then each one of those could count as a configuration of the atmosphere at any point in time. So each one of those would be an omega. Then in the phase space, I have a collection of maps that are going to be parameterized by these configurations, and my phase space I'm calling M. And to continue with this atmosphere example, M might be physical 3D space, so it might be the physical 3D atmosphere. And if you give me a configuration of high and low pressure system, then this will determine a wind field, and that wind field will move around air parcels in the physical 3D space. So T omega could be the map that maps an air parcel from where it is now to its location in 6 hours' time. So that's a map on the physical 3D space. Okay. Now, if you want to run your system non-autonomously, then you would start with the current configuration. You would apply your map T omega on your phase space. After that time, your configuration has updated so you need to update with sigma, and then you apply the map that corresponds to the new configuration, and so on and so on. And so if you want to run this n steps, then you have what's called a map co-cycle. And so this setting has been developed over many, many years by many, many people. And I'm just going to mention Ludwig Arnold, who really, from Bremen, who really did a lot on this in the 70s, 80s, and 90s, and has a fat encyclopedic but very good book on the topic. And also Michael and one of the organisers, Michael Cheprin, have pushed this quite hard in the climate direction, so taking these ideas and trying to apply them to climate. Okay, so here are some examples to show you what you can do with this setup, and these are more mathematical examples, but in the first two I want to contrast the different types of driving you can model. So in the first example, I want to model a single map that is perturbed in an IID way by some small perturbation. So one way you could do this is you could say my configuration space is a bi-infinite sequence of intervals minus epsilon to epsilon. So I just have infinitely many copies of these. My sigma is going to be just a shift to the left, and my p is going to be a product of scaled Lebesgue. My T omega is going to be very simple. I won't specify it exactly. Let's say it's a map of the real line, and T omega is going to be some fixed map T plus the 0th entry omega naught. So what does an element of omega look like? It's a bi-infinite string of numbers between minus epsilon and epsilon. I look at the 0th or the central entry, and that's what I just perturb by addition here. Now as I shift, I'm going to proceed along my sequence. And so this setup models IID uniformly distributed noise in this range applied to a fixed map T. Okay? So memoryless perturbations. On the other hand, at the other extreme, if I want to have some similar sort of perturbations but with high memory, then I could say omega is a scaled circle, sigma is an irrational rotation, a rigid rotation on that circle, and P is again scaled Lebesgue. So my map T is again, my T omega is T plus omega, and then I'm subtracting epsilon because elements of this circle lie between 0 and 2 epsilon, so if I need to have them between minus epsilon and epsilon. And this setup models highly correlated noise. It's still uniformly distributed in this range, but it's highly correlated because this rotation map is in ergodic theory, we would say it's ergodic, only it's not mixing. It has very strong memory, and so it's, in a memory sense, the noise here is the opposite of what you have here. Here it's memoryless, here it has very strong memory, but it's still uniformly distributed. Okay, and something more general, you could have omega being, and this is going to come up later in the talk, omega could be the Lorentz attractor, and sigma could be, say, the time one map of the Lorentz flow. My measure P could be the SRB measure, the Sinai-Ruel-Bowen measure of this flow, and T omega could be some general family of transformations depending in some general way on omega. So they're parameterized by this point in R3, which lies on the Lorentz attractor. And here you could say that the phase space dynamics is driven by moderately correlated noise because the Lorentz dynamics is mixing, but it still has memory. So it lies somewhere between these first two extremes. Okay. Okay, so that's non-autonomous maps on the phase space, and now I want to move to densities on the phase space. So associated with each map T omega is a linear operator called the transfer operator, and I'll call this P omega. And this involves mass distributions on the phase space in the same way that T omega pushes individual points around. So for example, going back to the atmosphere, if T omega is describing how an individual air parcel moves in phase space 6 hours forward, then P omega would describe, let's say you're considering not a single air parcel, but some larger region in your phase space, and you have some let's say, concentration of some inert chemical or mass of some quantity, and you want to push that entire concentration forward, then this is what this operator P omega does. Okay. Now, as we had a map cocycle back here, okay, if we wanted to go n steps, I can replace all these t's with p's, and I can make a transfer operator cocycle that is going to push forward densities n steps in a non-autonomous way. Okay. So for general driving dynamics and suitable phase-space dynamics, you can say something mathematically about this. So in the expanding case, if you took, for example, a constant distribution represented by the constant function 1, and you push this forward, you get you converge to a family of functions that I'm calling H omega. So this is you're pulling back n steps and then pushing forward to the present. So Vous did some work on this in the late 90s and 2000s, and particularly in this very general driving dynamics case. Earlier work was on situations with less general driving. These densities obey an equivariance relation. So if you take the density at time omega and you push it with the omegath operator, then you get the next density. And they're stable to deterministic, stochastic, and numerical perturbations, all of these reasonably general, in the case where the map is expanding. Okay? That's also the case I'm talking about here in Vous. This is the case where the map is expanding in all phase-space dimensions. Okay. So I think Michael's probably going to say something about invariant densities, so I'm going to not say any more about those. And I want to move on to signed densities, which is going to be the rest of my talk. So I want to talk about decay rate of these as I push, of these distributions as I push forward. Now if I take one of these H omegas and I push it forward, its decay rate, its exponential decay rate is 0, because how would I measure that? Well, what I would do is I would take my h omega, I would push it forward, I would measure its size by taking its norm, and then for the exponential rate, I'd take a log and divide by n. Now, because of this equivariance here, if I do that, all I get is a bunch of 1s, and I just end up with h n steps later. So the size is not growing or decaying exponentially, and I end up with a 0 for my decay rate. It's about the same, so it's not decaying. Okay? On the other hand, if I take a sign density, let me call that W, then this can have negative decay rate. So if you push this forward, you can get these, you can get multipliers, random multipliers that can be less than 1. And you can find, in fact, a smallest non-random decay rate, which is a Lyapunov exponent. Let me call that lambda. This is negative, and a corresponding set of random equivariant functions. So they're equivariant in the sense that you take the omega-th one, you push it forward, you get the next one. And so this lambda, which is negative, we compute as this. And you have this ergodic theorem that says that this is equal to the integral of the log of all these multipliers up here with respect to your invariant measure. Now, the existence of the lambda and this family W come for mathematically for suitable T come from a theorem called the multiplicative ergodic theorem, originally by Osledadz, and we have worked on with Simon and Anthony and Cecilia. Extending these to the case where you have non-injective operators, and you can apply these to transfer operator settings. Okay, so what does this have to do with fluids and geophysical fluid flow? So because these Osledadz functions represent families of functions that decay very slowly, there must be some features embedded in them that are also decaying slowly, and these features are features that we're going to be interested in the geophysical setting, because they are features that are not mixing in the fluid very quickly. So here is a plot of, so there's a cylinder, so the left and right edges are periodic. We are driving this by the Lorentz equations, so in the background you have the Lorentz equations driving this nonlinear cylinder flow. And if you see the color scale here, orange is 0, red is negative, and yellow is positive. And so this is the graph of a 2D function. And these highlighted objects here tell you the objects, these highlighted regions tell you the regions that are not mixing quickly. So as I push this forward, this is what these frames are. As I push this forward with my transfer operator, this is at time 0, 2.5, 5, 7.5, 10. You see what happens is these disks precess around the cylinder, but they're not mixing in the fluid. And to demonstrate the equivariance, this is at time 10, and so to get this, I pushed forward this computation at time 0, 10 steps. This final frame, this is an independent computation at time 10, and you see it looks basically identical. So this is demonstrating the equivariance relation that I mentioned earlier. Okay, so that was the functional view. This is the phase-space view. If I now make gray and black these sets that I had earlier here, and now evolve with the flow in phase space. Additionally, I've added two sets here and nearby, just randomly positioned. As I flow this forward, you see that the randomly positioned sets very quickly mix throughout the cylinder, whereas these gray and red gray and black regions, they are mostly traveling along. Here you see they start to filament a little bit at the edge, and here in this very last frame at 50, you are filamenting a little more. But mostly they're staying together. They are decaying much more slowly than a randomly chosen set. Okay, so these these oscillated functions and the upper limit exponents, these are infinite time constructions, and you might be interested in certain time scales, or you might have a finite amount of data to work with. So what about finite time? Can you do something there, something similar? Well, the natural thing to do is to simply not take the limit, so to consider the same kind of decay relationship. So you have a sequence now of transfer operators, but now only up to time n. And what I want to do is find a function w omega so that I push forward to some future function with some multiplier, and I want this multiplier to be as close to 1 as I can. Okay? Now, if I'm working in some kind of Hilbert space, then the way to solve this problem is reasonably straightforward. You want this lambda to be a singular value of this concatenation, and you want this w to be the corresponding singular vector. And so this is going to give the slowest decay in finite time. And in particular, this singular value lambda is quantifying the slowest decay from time 0 up to n. Okay, that concludes part 1. So part 2 is I want to continue with this idea of finite time flow, but I want to do it through geometry because, well, on the one hand, it's very mathematically nice and interesting, but on the other hand, it leads to algorithms that are much more data efficient than the probabilistic methods. Okay, so here is a sketch of mixing from a geometric point of view. So suppose I give you a set in 2D, and here are 3 possible future evolutions, and I ask which of these 3 evolutions corresponds to greater or lesser mixing. So most people would say, well, A looks like it's getting mixed less, and the reason they would say that is because these look like they're starting to get elongated and filamented and mixed. You know, potentially they will later get mixed through the phase space. So mathematically what is going on here is the boundary size is getting long relative to the enclosed volume. And the boundary size is the interface. I mean, how does mixing occur? Mixing occurs, one view of how mixing occurs is you have some small background diffusion, and that background diffusion is pushing you in or out of some interface. And here the interface is the boundary of a set, and if that interface is getting long, then you have more opportunity for diffusion to kick you in or out of that set. Now, in differential geometry, there's a branch called isoperimetric theory that is concerned with sets of minimal boundary size relative to volume. And what I want to just sketch here is how you can adapt this to a dynamic setting. So what I'm interested in is sets that have persistently minimal boundary size. So as you have a set and it's evolved nonlinearly under some nonlinear dynamics, the boundary remains persistently small. So to come back to these frames I had earlier, you see these disks that I identified. Initially they have, well, all of them actually, all of these have pretty small boundary to area because they're all disks. But as I evolve these, you see the ones I identified, their boundary to volume ratio remains small, but the randomly chosen ones, the boundary to volume ratio blows up because the boundary is getting very, very long very quickly. Okay? So if I were to search for sets that had persistently small boundary to volume ratios, this would identify these types of sets that I'm looking for. Okay? These are the ones that are going to dissipate most slowly. Okay, so I'm going to use the Laplace operator, and so it's well known in differential geometry that there are strong links through spectral geometry between Laplace-Beltrami operators and the geometry of manifolds. Maybe the most well known is the Cheeger inequality. So if you want to separate a manifold into 2 pieces, one of the pieces being a set A, this ratio of the size of the boundary of A and the volume of either A or the complement of A, whichever is smaller, is bounded above by the first non-trivial eigenvalue of the Laplace-Beltrami operator. Okay, so this gives you a lot of information about the manifold. You can adapt this inequality to the dynamic setting that I'm describing. I won't mention that here, but this is based around a dynamic version of the Laplace operator, which is essentially a pushed forward version of the Laplace-Beltrami operator. So you can view this two ways. So one way is you're currently at configuration omega. You have a function you want to act on. You push it forward in time, k steps. You apply Laplace in the future, so it feels the deformation that has occurred due to the push forward. And then you pull back with the adjoint to bring you back to the omega fiber. So that is what is happening here. And you average all these operators from k is 0 to n. And each of these is elliptic and symmetric, so you end up with an elliptic symmetric operator. It has all the nice spectral properties of the usual Laplace operator. A geometric way of looking at this is you have the Euclidean metric copied into the future, and you pull this back as a pullback metric to the omega fiber, and you average all of those Laplace-Beltrami operators for those pullback metrics. Okay. All right, so with this, we want to find eigenvectors of this in analogy to the static isoperimetric theory case. And if you have a complicated manifold, the standard way that you would numerically approximate this is with finite elements. So this is what we do. We make a special finite element approach for our dynamical setting. And the only data we need are positions of trajectories. So what we have in mind is that you have trajectory data, and that's it. So you know you have some trajectories, you know where they are in phase space. We want to find where these coherent sets are from the trajectory data, and we're going to do this by building this dynamic Laplace operator and looking at eigenfunctions. The data can be scattered, it can have missing pieces, and most importantly, it can be sparse. So in the geophysical setting, we're thinking of these trajectories as coming from, say, drifters in the ocean. Okay? So you don't have very high resolution coverage if you're using physical observations like drifters. We don't need any phase-space derivatives, which is, of course, advantageous. So here is a sketch. So this is the Gulf of Mexico. So you might have some buoys. In fact, these are real buoys in a real experiment. At this time, you mesh them up. And of course, you have their positions at several times, and you make several meshes. And you combine these several meshes to make your estimate of the dynamic Laplace operator. And this is what you would compute as an eigenfunction. So you would look at this and you would say the extreme values are red and blue. So you have a non-mixing region here and a non-mixing region here. So that's just a sketch. I'll show you some real examples shortly. Okay, so the first of these is tracking Agulhas rings. So these are well-known objects that form in the Indian Ocean and move along the Agulhas current out into the South Atlantic. And they are carrying salt and heat from the saltier, warmer Indian into the fresher, cooler Atlantic. And oceanographers are interested in how much of this heat and salt transport is carried out by these rings. So if you had an efficient automatic way of finding these rings and calculating the transport, this would go some way to answering questions about heat and salt transport from the Indian to the Atlantic. Okay, so the experiment I'm going to show you is using Vous satellite altimetry. So the satellite records sea surface height. The sea surface height is interpreted in a geostrophic way to derive a velocity field. And we are going to analyze a small rectangle centered on this pin. The data that we use looks like this. So that's the rectangle, that's the initial rectangle. And then this is 90 days of the flow, so we want to find some eddies in this flow. And in fact, we're not even using all the movie that you see here. We're just using the points at the initial time and then at the 90 days later. So we just have 2 frames. And so using those 2 frames, we compute this operator. These are the first 3 eigenfunctions. And so you see highlighted here something red here, and something red here. And so if you extract these 3 red objects, you get 3 objects here. And this is how those 3 objects flow over the 90 days. So each of the grey objects, its boundary is not growing over the flow duration, okay, as we wanted, okay. The blue set, on the other hand, which was just randomly thrown down, its boundary is growing very quickly over the flow duration, okay. So this is working nicely. We're finding the sets whose boundary does not grow, which are the eddies. Okay, and now the last part is about what you can do if you want to find lots of these objects at once. So a couple of slides ago I said here are the 3 eigenvectors, and we extract these 3 grey objects. Okay, so how do you do that in a more consistent way? And if you had more objects, how would you do that? So maybe I'll just take a step back for a little to talk more generally about operator methods. So operator methods in dynamical systems, usually you have operators that are of, let's say, Markov type, meaning the spectrum is inside the unit disk in the complex plane, or of Laplace type, where the spectrum is in the left half of the plane. The examples of Markov type operators are things like transition matrices and the transfer operators that I've been talking about. And Laplace type examples, they could be generators of flows, the dynamic Laplacian I introduced, or other Laplace operators. You could also consider what I'm calling non-dynamical data analysis methods like EOF, POD, or other SVD-based methods. In each of these cases, a spectral analysis involves computing eigenvectors or singular vectors in order to find modes of various types. And these modes are usually meaningfully ordered by the spectrum. Okay? And each of these modes has several distinct features, and often the distinct features in these modes are the extreme, normally the extreme values of the modes are what you catches your eye and what you want to look at. So how do you take out these distinct features? How do you separate these distinct features from several modes? Here's a toy example from geometry, so there's no dynamics here. I've made this artificial manifold where I have a large disk and I glued 4 small disks around the outside, and then I just applied the usual Laplace heat operator to this manifold with 9 boundary conditions. And so the first 4 eigenfunctions you see here, so the first is constant, and then these are the next 3. And you see that it's kind of it's trying to highlight these little disks that I glued to the outside. Right? And they are highlighted in different ways. And so you might say, well, clearly these 4 disks are the important things. But what you would really like is to have something like the lower set of vectors, because each of these vectors has just one of these 4 disks in each of them. Yeah? And I don't want to force a partition of the phase space. It's kind of clear from the above that the big disk is not as important, is not as highlighted as the small disks. So I don't necessarily want to include the big disk. So the solution is going to be take this eigenspace, take the space spanned by these 4 vectors, and rotate it to get a best approximating sparse space. Okay? And why sparse? Because I want to have minimal support, just one feature in each of the vectors. Okay? So minimizing the support is consistent with sparsity. Okay, so here's a sketch of how this goes. So we call this sparse eigenbasis approximation, or CEB. So let's say you have R of these vectors. You stack them up in an array as columns. Usually R is much less than P. So in my example here, R is 4, and P is, I think, 10,000. So it might be the number of, P is the number of pixels you have, say. So this array V, this is something that's very long, very tall and thin. And the main idea, as I said, is you rotate this R, which is relatively small, dimensional span of these long vectors with an R by R orthogonal matrix, so they become as sparse as possible. And each rotated column now should contain a single feature. So we want to solve a standard kind of sparse problem, which is R is your rotation matrix. You want to find a basis so that when you rotate it by R, you get something that's close to V. So this is the Frobenius norm. So this is your approximation error. And this 1-1 norm is measuring the sparsity of the data array S. So this is your sparsity penalization. Okay, so this is fairly standard. The way, I won't go into the way we solve this. It's an iterative method where you solve each of these problems individually. So what we've done is we've specialized and added to ideas from Journet and Vous et al. Vous et al. In fact specialized this, which was very, very general, and we've specialized further and added some things to that to fit our setting. Okay, so on the ocean data, here were the first three vectors. They look different. The color scheme is different to before, but they're the same as I showed you before. And after its rotation, then you get these nice, clean one object per vector pictures. And of course, now you can just add these by vector addition to make a composite image. Here's an example from 2D turbulence. So this is Navier-Stokes on a 2 torus. Here I'm computing the 2 leading singular vectors of the transfer operator, so this is using the method from the first part of the talk. There's no boundaries, so the first eigenvector is constant, and this is the second eigenvector. And so normally you would look at this and say, well, okay, you have some extreme red here and extreme blue here. But by rotating this 2D space, you can make this much clearer. So this blue feature here is rotated into something that's close to 1 here, and these two are rotated to these. And you can add them together to a single image. You can do more features, so the more vectors that you include in your subspace, typically the smaller the scale of the features that you pick up. So here are 7 features. Now here I've already made, these are composite images already. I've already done the rotation and made the composite image. This is the initial time. This is showing coherence. So this is the initial time. This is a flow 50 units later. So all the objects have moved around. The ones I've identified, they are the coherent ones. In the background you have turbulence because this is turbulent Navier-Stokes. And you can do here's 21 features. Okay, so again, this is time 0. This is the future, and again, the boundaries of all these red things are not getting very long. But in the background, actually, I haven't showed this here, but the background is mixing very quickly. Okay, so yeah, so we can use sparsity to disentangle distinct features. We don't impose domain partitioning. We also propose in this paper rescaling of the spectrum for clearer eigengaps. That I think is a very sensible thing to do, and there's code on my webpage which is very short. So now I want to show how this works for a flow in the North Atlantic. So this is again using a Vous satellite altimetry to derive the velocity fields. I'm going to use 56,000 trajectories. The trajectories were kindly provided by Irina Rapina from Woods Hole, and let me show you some movies. Okay, so that's the original set of points, and I think you know where you are. This is New York. This is Nova Scotia, and then you run. And so we want to find eddies or other coherent features in this flow over this 90-day flow period. So the first non-trivial eigenvector is looking like this, and this is very nicely separating the Gulf Stream. So this sharp delineation between blue and red. So you see this meandering separatrix interface, which is remaining short. I mean, it's remaining short throughout the flow time, and yeah, it's highly correlated with the Gulf Stream. So here we have a purely kinematic, we're only using point positions of particles, a purely kinematic diagnosis of the Gulf Stream. And if we use more eigenvectors and make a composite, set of frames as before, then we can pick out a bunch of eddies. So again, the boundaries of each one of these red objects is remaining short throughout the flow time, which is what we wanted because we wanted.
Can you say what is constant? What is the quantity that is constant? Whether it's units?
Sorry, who's asking? Can you raise it?
What is the quantity that is contours? What are its units?
The units are non-dimensional between 0 and 1. So you could think of them as likelihood of belonging in an eddy.
And blue is towards 0?
Blue is 0, and that is also, yeah, I mean, blue is 0, and the deepest red is 1, and you can think of this as likelihood of belonging to an eddy or some coherent feature. This is just to just to illustrate the. So these are examples of two eddy estimates that we get, just to show that you get nice smooth estimates from relatively sparse. I mean, the black are the data points. I didn't try to optimize reduction of data points. I could probably get away with less, but it's not super high resolution compared to the estimates that you get. Okay, and this is my last slide, apart from a movie. So now I want to show that you can do this at a global scale. So I'm going to show you what we did is we took the globe, we meshed the entire globe, putting direct lay boundary conditions on the coastlines, and we had 5 years of flow. And we wanted to see with this many particles, which is not particularly high resolution. It's half what I just showed you before. We want to find what are the slowest mixing global ocean structures over this 5-year period. We actually used I think, is it written here? I think we used a 100 meter below the surface level, so not at the surface. And you'll see in the movie that we pick up the Weddell and Ross gyres, which are Antarctic gyres. We pick up the southern flank of the South Pacific gyre, the subpolar gyre, the Greenland Norwegian Sea, and the same Gulf Stream separation I showed you earlier. Okay, so on the, let me explain, on the left, this is just coloring by longitude, so there's no computation here, it's just to show you how the flow is going. Okay, oceanographers like to see flow by longitude. And on the right is the computation. So on the right, again, the color scale is from 0 to 1, and 0 being not in some coherent feature, 1 being strongly in some coherent feature. And so here you have the Weddell and the Ross gyres. This is the southern part of the South Pacific gyre. This is the subpolar gyre. Here you see the Gulf Stream separation. I mean, it's weaker than before, but it's consistent with the earlier computation. Although this is a 5-year computation, whereas before we had 90 days. And we see this Norwegian and Greenland Sea here. So this is reasonably fresh off the computer, and we haven't don't have a full analysis of this, but I'm pretty encouraged by the results. And
the North Equatorial counterpart, which is in the Pacific.
Which one? Do you want to point to it? It's the top one. The top one. Here. Yeah.
Yes, you see the current, the equatorial current system
yes,
in
yes.
the tropical Pacific. So
yes. And that's it. Thank you for listening.
Yes, thank you for this nice talk. 2D flow is very special because phase space is equal to real space in some sense. So what would happen if I was doing that for 3D turbulence? Then the phase space would be 6-dimensional, and what would this structure correspond to?
Well, I would try to do it in 3D space.
So you would do it in the physical space, not in the phase space?
Yes.
Okay, but in 3D turbulence, you don't have such long coherent structure.
That's right.
Okay, so maybe it will not give anything.
Probably not. Okay. Yeah, yeah. I mean, you could, if you did in the 6-dimensional space, then what you would be looking for are features that remain nearby in the physical phase space, and their momenta is also remaining nearby, right? So it's a different question.
An important question is usually how many components to include.
Yes.
Do you have some criteria, or do you make it by hand? Or?
Yeah. Yes. You mean like how many here to include? Yeah. So yeah, this is a problem. I mean, when you do spectral analysis of real data, then typically you don't see any clear eigengap. Yeah. And so we did work on this, and so I mentioned there was a rescaling that we think is very, if you have some idea about the dimension of your manifold, then there is a very natural rescaling that you can make, and we think that is useful, and that's in the paper. And also, you can make these computations. It's very fast to make these these sparse rotation computations. So you can test that over many different dimensions of your subspace, which are essentially choices of how many features, and you can see which ones have small error and therefore have a natural decomposition. Yeah. So we proposed those two in the paper.
Yeah, I have a question related to the first one that was raised, which is the 2D versus 3D issue. Because your estimation of the coherence of these eddies is based on a 2D field, but the actual velocity is 3-dimensional, so you cannot be guaranteed that particles aren't actually escaping through the vertical velocity and not staying in what you think is the coherent component. So I was wondering if, obviously it's not possible to do it with the VISO data because you have 2D velocity fields, so. But with this, if I understand correctly, this is a computation, this is a model, right? So you do have 3-dimensional velocity. And so I was wondering if you could give us a sense of the error that is made by using the 2D field as you did in this movie here, versus if you had used the full 3-dimensional field, whether the probability of coherence map, how different would it look?
We did, so in the computation, I mean, we knew about these problems. In fact, we saw them when we vectored the particles. So I think in this computation, my student, I don't know all the details, but I think we decided on having 5 levels that were spanning, I think, around 100 odd meters, and I think we were advecting all of these and then collapsing them to a central level to get a 2D result. So that doesn't answer your question about the error, but you have if you have flow. I mean, just to tell you another problem, if you have flow on the surface, then as you know, particles are going to go down in some areas, yeah, and you'll get an accumulation of particles in other areas. So if you just make a flow on a surface, then you'll get bare patches where particles have descended and you have none, and you have upwelling areas where particles want to go away from. So we're still trying to figure out what is the best way with a model to get a nice, consistent, uniform spread of particles. Yes, yes, yes.
So I don't know that you're correct, and the spiral doesn't have the same. It's actually centered on the western side, the ones that go down.
Yes.
And similarly, the ones that go up. So it's very heterogeneous in 2-dimensional space, the vertical structure. So I don't think averaging at fixed levels is very...
No, I'm not saying it's the best. I'm happy. I'd be very happy to talk to you afterwards to find something good. As I said, this is our first experiment. So, yeah.
Maybe one last question. Yeah, hi, Roberto Buizza. So at the European Center, we have been using singular vectors for 25 years or more to initialize the ensemble system. And singular vectors have been computed using a short time interval, say 24, 48, 72 hours maximum. We never really were able to go longer in time because when you compute them, you need to assume linear evolution around the flow-dependent trajectory, but it's still a linear evolution. So we were really never able to extend the time interval of computation because of this. Now here, if I understood correctly, you're working over a long time interval. It's true that you're looking at the singular vectors with the lowest growing, while at European Center we were interested in the fastest growing. But I still wonder whether the approximations you need to rely on when you use a singular vector technique, which is linear evolution, is valid for such a long period. So did you check that the structures you find when you non-linearly evolve them back into your model actually stay coherent as you find them with your computation?
Excuse me. So to answer the last part, what you see in the movie is the evolution over the 5 years. So if you think the red stays together, then the answer is yes. As for your earlier remarks about singular vectors, I think, so you said, I didn't quite catch, you said this was to initialize. I don't know what your application is, but the Osleditz vectors that I was talking about before, this is a way to formalize the equivalent of singular vectors over an infinite time, and you can approximate these. I mean, there are numerical methods to estimate these, which are robust, and so you could use those. What you typically find is that they're pretty close anyway to, especially with the large growth singular vectors. They're pretty close anyway to these singular vectors. So because I mean, once you've already grown a lot initially, then you will continue to grow. I mean, I can tell you a bit more about that, but I think what you're probably doing is pretty good already. Yeah.
Gary, this was an amazing talk. I mean, everything from dynamical systems to PDEs to this. I just wanted to emphasize a few additional features that are incredible. I mean, you have the so-called fine ladder jet, the Somali, the Great Whirl in, off the coast of Somalia, which has a seasonal change in rotational direction, which is just what happens. And the earlier movie that you showed with the Gulf Stream usually splits into an Azores current and the North Atlantic drift, and you caught an episode where the Azores branch is stronger, in one of the, and it's just really beautiful. I mean, congrats.
Thank you, Michael.
Maybe